lecture will be about human-AI interaction in healthcare. So I'm going to start with, if this lets me start. Okay, 1 second. I'm going to start with a nice picture. So in this class, we've spoken a lot about the promise of AI, how AI can improve decisions. We've seen examples of decision support tools, and you've built yourselves algorithms to predict length of stay, sepsis risk, and more. And the picture we'd like to imagine in our head is maybe clinicians have this much accuracy, and through our fancy AI tools, we've improved on clinicians. And the hope is once we put clinicians and AI together, we'll get something that's better than both. That's kind of the promise of all of machine learning. But the reality is not that case. Often in practice, what we see is once we put AI and clinicians together, we get a performance that's worse than just humans on their own or AI on their own. So that's kind of the fundamental problem of this field. How come AI integration is not helping us as much as we'd like it to? And in today's lecture, we'll talk about why we have a frowny face, why this is happening, and how we can turn that frowny face into a happy face. So let's get started with an example. We want to predict from chest X-ray if a patient has atelectasis. So atelectasis is when part or all of the lung collapses, and this could be due to the presence of mucus or foreign objects blocking the airways. So what happens is you have the patient X-ray, you have the patient's medical records, the radiologist will look at these two and will make a diagnosis, and they will write the radiology report. You've taken this class, so you think, maybe I can do better. So let me try to build a model to predict atelectasis. So a student from class decides for their project, I want to switch, I want to predict atelectasis from chest X-rays. Lucky for you, we have a massive data set of chest X-rays and diagnoses of atelectasis. This data set, Checkspert, was created by people from Stanford, and they took radiology images and radiology reports and extracted from the reports annotations indicating the presence of atelectasis. So these labels are a bit noisy, but they suffice for accurate predictions. Then you use kind of a fancy deep learning model, particularly ResNet. So ResNet is a type of convolutional neural networks, where at each convolutional block, you have a skip connection where you feed in the input originally. This is a bit old, so now we have fancier methods, but this suffices. You trained your model on this data set, and now you're ready to evaluate. Can I do better than my radiologist? So you build a very careful test set. You gather 500 images. You get 5 radiologists to predict on each image, and you let the ground truth be their majority vote. So maybe a radiologist alone is not enough. You combine 5 together, and you get a really gold signal of whether the patient has atelectasis. Then you get 3 radiologists other than those 5, and you tell them to make predictions on this test set. And what we're going to do, we're going to compare the performance of our model compared to these 3 radiologists that we left aside. So you plot the AUC curve for your model, and then you get pretty high AUC. And now you want to see how does the radiologist compare to your model. When you visualize the performance of the radiologist, there are going to be points on this plot. They're not going to be a full curve because the radiologist has a specific operating point. For each patient, they're going to say, you have atelectasis, you don't. So we cannot plot a curve, but we have a single point. Now from this curve, can we say something about AI versus human performance? Does anyone can conclude whether AI is doing better or it's inconclusive? So the AI is actually doing better than all of these radiologists. And you can understand that from the following. So each radiologist has a specific true positive rate and a specific false positive rate. So radiologist 1, for example, has about a true false positive rate of 0.8. For that same true positive rate, the model can find an operating point that has a lower false positive rate. So it's strictly better. And it's doing so for all of these radiologists. So wonderful, you've beaten the radiologists. So let's get rid of radiologists. And kind of the question we're going to ask is, what happens if we take away the radiologist or the clinician and replace them by an AI model? And how do we integrate this AI model into practice? So the lecture of today is going to start by understanding how we integrate models into practice. And then we're going to understand the pitfalls of that. So once we deploy the model on its own, it's going to completely replace the physician, the radiologist. So you have the X-ray, you have the model. The model can even try to regenerate a report on its own. And then you take that report and you feed it to the physician. So often radiologist is a middle ground. So the radiologist will create the report, but who makes the final decision? It's the referring physician. So just an in-between. We're going to do a case study on diabetic retinopathy where this actually happened. So diabetic retinopathy is a diabetes complication in the eyes and can often cause blindness. So you can see kind of here 2 images of healthy retinas and diseased retinas. In fact, I once trained in an experiment lay people to see the difference between these 2 images. And if I give you enough examples, you'll actually do much better than chance on this task. But it takes a lot of practice. Why do we need AI in the first place? In places like India, where you have almost 70 million people who have diabetes, there's not enough ophthalmologists to diagnose them. And often, people can wait 2 months to get their results. And they have to travel far away to even see the ophthalmologist. People from Google built a model to predict diabetic retinopathy from images of retinas. And this model can improve the false negative rate of clinicians by 23%, but albeit it will increase their false positive rate by 2%. So there are trade-offs there, but it's clearly almost good enough. So they took this model and they deployed it in 8 sites in Thailand. So this was a study over a year and a half, and you have almost 8,000 patients who were given predictions by this AI model. So the clinicians, the people, go into these small sites where you have a nurse who's equipped with a camera. The nurse will take pictures of people's retinas, and then the AI model, in almost 90 seconds, will make a prediction for this particular patient. So the promise of this study is that before AI, it will take almost 2 months to get a prediction. People will have to travel, then the ophthalmologist will have to look at the image, and then you have to send back the results. With the AI model, hopefully, you come in same day, you might have to wait a few hours, and then we'll give you diagnosis immediately. So what happened when this was deployed? The model actually refused to make a prediction on 20% of patients. So when the nurses were taking these images of the retinas, there were so many problems that they were facing. Some of the cameras were old. The lighting conditions were really bad. So they had to, cover up the camera and do so many tricks just to get it to make a prediction. And you have limited time to make sure you get the perfect image because patients are coming in and out. And when they asked the nurses, what did you think of this AI model? Often nurses said, well, it's not as good as I thought it was. I can read the images, but for some reason, it can't read these images. So it's not as accurate as you might think. And so now those that, they came, they wasted their time, they waited in the office, and they still can't get the prediction. So they have to go and travel back. So this is a problem that the designers of the system never imagined. And this tells you that you really need to understand how your model will be used. You need to understand the protocols surrounding the deployment of the model. If you don't take that into consideration, all your promise will fall. And to evaluate the model, you don't not just need to get your test set and get your AUC and be happy with that. You need to go into the clinic, see the predictions, and see how it's affecting people's lives. And in this setting, when we eliminated the ophthalmologist, one can think that, if the model fails, what will happen? So there's a clear case where, for example, suppose the people in Thailand, some foreigners come and visit, and the model is not trained on people outside of Thailand. And the whole of the classifications will fail. So there's no safety checks in case there if the model fails. We're going to talk about algorithmic solutions to this problem to begin with. So how can we take our model, take our ophthalmologist, and do better than both alone? So we're going to find kind of a middle ground between allowing the ophthalmologist to predict on their own and the AI on their own. The way we're going to do this is with algorithmic triage. So now we're going to build a meta-classifier, which I call a rejector. This rejector will take the image of the retina, and then will decide whether your machine learning model can predict, or whether you should defer your decision to the ophthalmologist. So instead of having the model predict when it's maybe not as accurate, you allow the model to say, I think you should really go and see an ophthalmologist. I'm not good enough on these cases. And we're going to see how we can build such systems. So we're going to start with this image. So from some input X, we're going to try to predict if you're healthy, if you're diseased. So we take our input X, our retina image. We're going to pass it through a neural network. This neural network will output logits. So these are, when you're training a neural network, before your softmax layer at the end, you have scores for each of the classes. Score for whether the patient is healthy, whether they have disease A, B, and so. So there are, in this abstraction, K different classes. And then you're going to normalize these scores to get probabilities. So you're going to get a probability for the patient being healthy, diseased, and so on. So you have this model, and you want to see how you can take this model and combine it with the human. So we're going to start with a warm-up. We're going to say, if there are points where we don't think the model is accurate enough on, and I would quantify this, we should abstain our prediction. So we take our classifier, we have these two decisions, make a prediction or abstain. The easiest way to do this is via thresholding the confidence of your model. So your model, you're going to see what is the class it predicts. It predicts this person has diabetic retinopathy. You're going to see the probability it assigns for this prediction. For example, 80%. And what you're going to do is just threshold that prediction. So if it's below 80%, we're going to send you to the ophthalmologist. Otherwise, we're going to make a prediction. What's the problem with this? Is that we're not modeling the ophthalmologist. The ophthalmologist is not some oracle. They make mistakes themselves. And to have a perfect system, we really need to model the error boundary of this ophthalmologist. So how are we going to do that? The first thing you might think of, what if I model the ophthalmologist's decision-making? How they make predictions. So given an input X, I model their own probability function. What would they assign the probability of this patient being healthy? This is a thing that's almost impossible to build, because building this task is almost as challenging as predicting the patients. So what we're going to do, we're going to do something clever. Instead of trying to predict their decision-making, we're going to predict where they make errors. And this, I will claim, is a much simpler task than predicting how they make decisions. In the simplest case, suppose the ophthalmologist is perfect. For us to achieve this perfection, to model this perfection, we need to actually classify the task perfectly. But if we just care about their error boundary, we can just say they're perfect everywhere. So it's a much simpler task to optimize for. So we're going to assume we have data that has our images, the predictions, and these ophthalmologist prediction. And we're going to build two models, one which is a rejector, which is going to decide who predicts, and one is the classifier that will make the predictions. So this is the picture we have in mind. Input, rejector, classifier, and expert.
Can you comment briefly? So what you described before was something where the model was a classifier, but then it refused to make a prediction for some fraction of the time.
Yes.
So here, the classifier won't even see it if the rejector thinks otherwise.
Exactly.
So I'm curious if you could sort of...
Yeah, so this is a generalization of that framework where you decide not to predict if you're not just unable to make prediction, but you also take into account the accuracy of your model, not just if you can make a prediction. So the failure case in diabetic retinopathy, like the image is not even readable for the model. Here it's one step above that. Even if you can read it, what's your estimated accuracy? And then comparing that with the ophthalmologist accuracy. So we're doing this modeling of both.
Flip the order where the classifier sees it first, and then the rejector basically is one of the options, I guess, from the classifier, where you can basically say, very clearly when you see it.
Yeah, so this is kind of the approach we will take in the end, so that we will build a single model that does all of this. But your comment is, I'm just saying this is a generalization of what they did. So this is just...
The rejector basically only looks at meta features such as...
It can look at everything. It will look at the image. It can look at the model itself. So this is just an abstraction for us.
It could, in principle, build the class or learn the classifier as well, and its confidence, and the doctor's likely performance on that case.
So
yeah, the rejector is almost the boss, if you wish, of the classifier. So basically, it's sort of...
Yeah, I will answer your questions with the next slide. You will see the approach we take. So what we're going to do, so these are not my slides, but they're about my work. So I'm not selling myself, but I am. So you take the image, you take the neural network, so this is as before, and you have the predictions for the K classes. What we're going to do is we're going to just add one more class, and we're going to call that the defer class. So we're going to allow our model to make K decisions plus 1, which is enabling it to defer. And then what we're going to do is we're just going to have the softmax as before, and we're going to make, if we're going to predict class 1, we're going to take the probabilities from the softmax. And then we're going to have a probability of deferral. So this P, this bot symbol, this is the probability that you should abstain from your prediction. And we're just going to do it from the model. So this is a very simple image. We did not modify anything from the architecture as before. We just added one class. But the problem is this is not a classification problem. In your data, you do not have a label that says defer. It's not available. You have to infer that. And the way we're going to do this is we're going to design a new loss function that, given that data and given this architecture, is going to actually output an optimal decision system. So the loss we're going to design is going to be as follows. It's a loss composed of two parts. The first part is going to be the cross entropy of our classifier. So almost the same as we're used to, but now instead of these K classes, we're normalizing over an additional class, which is the defer class. And then I'm going to add another term. So this term has this indicator on it. So this is an indicator which says, is the label the same as my expert prediction? Basically, is the expert correct or wrong? If the expert is correct, then you have these two terms, your classifier loss or kind of your rejector loss. And the system has to pick one of these two options. So these two things are normalized over the same quantity. And if you want to minimize this loss, you're going to have to pick one of these terms to set to 1, and the other will be set to 0. And you're going to have to learn that on your own. On cases where the classifier is incorrect, this right sign term will never show up, so your only choice is to actually classify. So we took kind of our problem from a classification of 1 to k, we added this extra class, and now we're going to assign kind of cost to predicting the classes and cost to deferring. And the cost of deferring is basically whether the expert got it right or wrong. And this is how we're going to build the system. Any questions on this? this is the last piece of math in this lecture. We're going to do more fun things.
Can I ask about the two symbols? What
Yeah.
is like thin square, and is that a ground symbol or something?
That's an I. It's an indicator function.
Yeah, this is an indicator if the y, the ground truth, is the same as m, the expert's predictions.
So the thin box is the contour of an eye?
Yeah.
I see.
Yes. We can prove fancy theorems on this loss, and one of them is that this loss is consistent. So if you optimize this loss, you get the optimal deferral system. Yes?
So can you one more time explain the rejector loss portion of this? So I understand that, like,
Yeah.
when like y is equal to m, and then basically when the model and the expert like concur. How does that relate
No,
to, like,
so this, when y equal to m, the expert is correct with respect to the ground truth. So now you have two options. Either you try to classify the label or you try to defer. And both of these are, a priori, both good enough. Only if you can actually pick the right label. So if this task is hard for you to classify, you can just maximize the right term and make sure you just defer. But on cases where this is 0, so you only have the left part, to minimize this loss, you really have to minimize the classifier loss. So you have to fit the label. Yes.
So the way I think of this is that log p bottom xn is essentially the system's estimate of how likely the doctor is to get this case wrong. And that's the benefit of this formulation,
Yeah.
is that it's not only learning its own decisions, but it's also learning how likely the doctor is to blow it. And so that biases it in favor of making its own decision if it thinks the doctor is going to blow this case. But that's the magic.
In
Yeah.
a way, the rejector is kind of like not just the boss of the classifier, it's also the boss of the doctor itself. And he basically says, based on what of my two components are going to do,
Yeah.
I will do something that maximizes the overall.
Yes. And it also drives your classifier to, be better at where the doctor is wrong.
Oh, that's so interesting.
So you're trying to complement.
So you can assign more strength.
Yes, so it's kind of weighting the points.
Wow. So in a way, the doctor is actually part of the option.
Yeah,
You're not replacing the doctor. You're basically saying,
exactly.
this is where the doctor does well, this is where the doctor does poorly, and this is where the classifier does well and poorly.
Yes,
But overall, I can optimize.
exactly,
Oh, that's so interesting.
exactly. So empirically, we have a bunch of experiments. This is on the chest X-ray data, and this was a result that was really hard for me to get. So I'm going to show you this curve. So the y-axis is the test accuracy. The x-axis is the coverage. How often does the classifier predict? So when the coverage is 0, the radiologist is predicting on their own. When the coverage is 1, only the AI is predicting. Somewhere in between is this perfect combination. And that's what the system is trying to get. And this curve is what the system can produce. And you can see the peak of the system is not at the extremes. It's somewhere in the middle ground. And it tells you can find a combination that does better than either of those two. So all right, if I've lost you, come back to me. No more math. We're going to do more case studies. So we saw that kind of triage can be really helpful if we build this system in mind. And this human AI system will reduce the time that the ophthalmologist predicts while ensuring better decisions. But what if the human had more time to make decisions? We're not constrained by the time of the ophthalmologist. So now we're going to think of another scenario to integrate the model, where we're going to put the model as a second opinion. So this is a case study on skin cancer prediction. You have lesions, and you wanted to predict them into 7 different categories, from the melanoma and so on. The classifier looks at the lesion alone and makes a prediction. We also have an explanation for the classifier's prediction. The dermatologist looks at the lesion on their own and looks at the AI's prediction and then makes a final decision. So we have 155 dermatologists who are making predictions on 28 images. And they make predictions with and without AI, and with AI predictions, with explanations and without explanations. And performance can really vary by what explanations we show them and which dermatologist is making predictions. So I'm going to start with a question. So in this study, they gave people two types of explanations. One is they show you the probability of the model predicting each of the different classes. The other type of explanations, the model retrieves images that are similar to the one you're making a prediction on and shows you what their true label is. Who thinks the dermatologist will perform better with similar images? Just raise your hands. All right, who thinks they will do better with multi-class probabilities? One person. Who is not thinking? So the results are actually opposite to what you all believed in. So with these similar images, the performance of these dermatologists did not increase at all. Even so, they took more time to make a prediction on each image. With the multi-class probabilities, you have almost a 13% increase in their total accuracy, and you did not add time when they make predictions. So this is a kind of a cool result. It's a bit counterintuitive, but we're going to dig deeper. So this plot shows you the following. The y-axis is how much did the dermatologist benefit from the AI. So 0 is no benefit from using the AI, and the higher the better. The x-axis is showing you the years of experience that the dermatologist has. So from less than 1 year to more than 10 years. The first plot shows you on images that the dermatologists were confident on. So if you're confident on an image, you can see the improvement for you is much less than when you're not confident on it. So when you're not confident on images, you really benefit much more from the AI. So it's helping you when you really don't know. So we think that's a good thing, right? But let's trick people more. So what?
It also hurt you more in a few cases.
Yeah, we'll get into that right now. So what these people did is the following. They had the AI predict with the regular predictions, and in some cases, they manipulated the predictions to be wrong. So we have cases where the AI is right, and the cases where the AI is wrong. And now we have the same plot. Y-axis is benefit of interaction. X-axis is experience. And here's this curve. So when you have the regular AI predictions that are often correct, almost everyone of some experience benefits from it. But what you notice that the people who are the most experienced benefit the less from it. When we have the incorrect predictions, the people who have no experience, they're hurt the most by it. And the people who have the most experience, know that this AI may be incorrect, or maybe they don't trust it at all, so they're not really harmed by it. So this shows you, the perils of over-relying on the AI, and also under-relying on the AI, because you may have benefited from it. So inexperienced raters benefited more from correct predictions, but were harmed the most by incorrect predictions. Vice versa, experienced raters benefited the least from correct predictions, but they were harmed the least by incorrect predictions. What is a hypothesized difference for this behavior? One is obviously the expertise. Another one I will talk about is your mental model towards the AI.
This is very cute because, in a way, your rejector before was building a mental model of how the human performs.
Exactly.
And now the question is also, what's the mental model of the human for how the AI performs? It's very interesting.
So now we're going to talk about mental models. So I'm going to define them in the abstract. What's a mental model? So a mental model is how we think something works. So it's not based on fact. It's more based on belief and experience. So it's not the same thing as what happens if I drop Peter's laser on the floor.
I wouldn't.
I know Peter will be mad, but it's a fact. It's more of my kind of how much did I think people were going to pay attention to this slide or laugh at this joke. This is kind of not fact-based. These are kind of mental models. What's special about mental models we have of AI systems? Well, I'm going to start with saying that our priors about AI systems are often wrong. We often think of them as acting the same way people do, but they don't. Moreover, it's hard to experiment and interact in an AI model. I can ask Peter, why did you do this? Why did you think that? It's a bit harder with AI models, but we're getting there. The third thing is that AI models are constantly evolving. They're changing their predictions. They're changing their knowledge base, while humans are more or less static. So kind of there's new thinking about mental models of AI.
I mean, we talked about prompt engineering before.
Yes.
And in the same way that, you could engineer prompts for the AI, you could also engineer prompts for the human. So by sort of offering also a view of the human of what you expect them to do, you could also manipulate human behavior.
Exactly. Exactly. So we're going to do another game. So this is another case study. You had radiologists and physicians, so people of different expertise. They were presented with a case report, and some of them were told it was written by an AI, and some of them were told it was written by the human. But what's the catch? Everything was written by a human, so we're only telling them it's AI or telling them it's human. So that's the only differentiating factor. And we're going to observe what do these radiologists and physicians rate this advice. So we're going to have another poll. Who thinks the physicians and the radiologists would rate AI as higher or human as higher? So who thinks they would rate advice by AI as higher? 2%. Who thinks we will rate advice by humans as higher? Okay, great. So let's look at these results. So let's look at the right side plot. So in colors, light, cyan, blue, and orange is blue is AI, orange is human. And the y-axis is the advice quality rated. The x-axis is whether it is a radiologist or a physician. So this is kind of the expertise. And you can see for radiologists, they rated the advice of humans higher than the advice of AI. And this is statistically significant. There's 2 stars. But for physicians, they almost saw them as the same. So they were not as impacted by what's the source of the AI. Then when you look at whether they're able to distinguish accurate from inaccurate advice. So the radiologists were much better at separating the accurate advice from the inaccurate advice. They were doing the task well. But you look at the physicians, they were able to do it better, but not as good. So that's maybe one, yeah.
So I'm confused because your setup was that all of the advice was actually written by people.
Yes.
So.
But some of it was not correct.
Right. So I understand the accurate versus inaccurate, but I don't understand.
Should the label be purported source of advice on the right?
Yeah, reported source of advice. So it's all by a human, but we just told you AI generated this report versus an experienced radiologist generated this report. So, clearly the only thing that made this difference is your mental model of the AI, of what AI capabilities are versus your mental model of radiologist capabilities. There's no difference in the advice itself, but we're still falling into a pitfall. So we can have this more formal definition of what a mental model is, and it's analog to the rejector definition we saw. And the way I'm going to define a mental model is basically your probability of using AI advice. And it's kind of analog to the rejector of the probability of deferring to the human, but now it's the opposite. It's a bit hard to measure this, but we have multiple ways to do this. One of them is looking at how often do AI predictions and human predictions agree. One of them is seeing human accuracy on corrected AI advice, incorrect, so that gives us a hint about the mental model, and more explicitly, just questionnaires asking you what your mental model is. So we're going to dig deep into what affects the mental model that people have of AI. So this is a really cool study. So this is a game that participants played. You see this object. This object has color, shape, size. And people are given two choices. You can use an AI system, so Marvin. If you use it and Marvin is correct, you get 4 cents. If you use it and Marvin is incorrect, we take away 16 cents. So your goal as a crowd worker is to get money. Your other option is just to say compute, and that gives you no money. So this is kind of the safe choice. And you want to maximize your returns as a participant.
I don't think I've actually understood it, I'm sorry.
Yeah, so people are shown this object. They're given features of this object, so what's its color, shape, size, and they can look at it. And they have two options. Either they can press this button called Use Marvin, and if it turns out that Marvin is correct, they get 4 cents. If it turns out that Marvin is incorrect, they are penalized with 16 cents, and we tell them immediately after they make a prediction.
What does the compute button do?
Compute button does nothing. You just don't get any money. So you avoid losing money if you don't think you're confident.
What does it mean for the object to be defective?
That's kind of the puzzle. You're trying to see if the object is defective. If you use Marvin, Marvin will answer and tells you yes or no.
But how do I know?
You will see after. So you make a prediction, and then we will tell you object is defective. Turns out object was defective.
Okay.
So this is a very simulated study. So you just make, I think you can just,
Is that the question?
yeah, sorry.
Why would anyone risk losing money? Like, 'cause you can lose 4 times more than what you can win. Might as well just not do it.
But if you know where Marvin is correct, you can just, maximize your gain. So it's a game. You can take risks. You can gain money. You can be safe. You can end up where you are. So you want to be rich? Let's be rich. All right, so abstractly, you can just think of it. I have this object, and I have 2 buttons. One button sometimes gives me money, sometimes hurts me, and another button just you don't get money. So this is the abstraction you have in mind. And basically, what we're going to do is we're going to manipulate where Marvin is correct and incorrect. And we're going to do it on 2 factors. One is the qualities of the object. So its shape, color, size. So for example, in this scenario, Marvin is always accurate when it's blue and square, and it's inaccurate otherwise. This is kind of a simple thing. And I can manipulate the probability of error given that it's blue and square. And I can change that from 0 to 1. And I have the opposite quantity, which is probability of error given it's not blue and square. And these are kind of my 2 quantities. If it's not clear, we'll go into the details now. So this is the first result I want to talk about. So let me re-explain it. So f is this logical function which says the properties of the object. So if it's blue and square, right? If it's blue and square, I have my probability of error. So this y-axis is the probability of error given that it's blue and square. And I'm changing it from 1 to 0.85 to 0.7. Ignore everything that comes after the first vertical axis. And I'm going to set the probability of error given that it's not blue and square. And I'm just going to set that to 0. And I'm going to measure what the payoff is of people who played this game. So the y-axis is the score you get from playing this game with the specific Marvin configuration. And what you see is as Marvin becomes more stochastic, so the region where it makes error is not, yes or wrong, yes or no. So if it's blue and square, it makes error or not. As this becomes more stochastic, so the probability of error if it's Boolean square, is actually not 1, it's 0.7. So sometimes, even if it's Boolean square, Marvin can still get it right. People are more tricked by it. So people get less score on this. So as the AI behavior becomes more stochastic, we perform worse with the AI. The analogy of this is maybe you're used to a calculator. You know where the calculator gets it right. If you use it, you know it gets it right. So there's no stochasticity in your calculator. But other objects that are more stochastic, you don't know when to rely on them and when not to. The other intuitive kind of explanation is, as this function f that we're defining, the error boundary of Marvin, becomes more complicated. So instead of blue and square, we can say blue and square and small, or blue and square, or red and large. This is a bit more complicated for you to learn on your own. So your performance decreases as Marvin error boundary becomes more and more complex. The third thing is, as you give people just more information about the object. So here we're not manipulating Marvin. We're just telling you the object is blue, its size is small, its shape is square, the temperature outside is 30 degrees. As we show you more stuff that could be irrelevant, your performance decreases. So we're just showing you more stuff. Nothing is changing about Marvin, but you are tricked more by thinking maybe it could depend on some of these things you're showing me. So by showing you things that are not useful, your performance is decreasing. The last thing, which is kind of very intuitive, if you actually knew what the error boundary of Marvin is, you're going to perform better with this. So this just, again, affirms that if your mental model accuracy is good, so you know where it makes mistakes, you're just going to get a higher score on this game. So the takeaways of this are as follows. Humans rely on their mental model to know when to use AI. This mental model can depend on many factors, including the stochasticity of the AI, so how random its behavior is, how complex the AI is, how complex is its error boundary, and how many features do I show you about the AI, kind of the size of the AI explanations. Any questions on this? All right. So now what we're going to try to do is, how can I get you to understand more about the AI and its error boundary? Because that's the key thing that's going to allow you to get higher scores in this game or in accuracy in real life. The solution we're going to think about is onboarding, which is basically training people before you let them out in the wild to know when to rely on the AI and when not to. So this is a study, okay, let's go to this. This is a study in pathology. So they recruited 21 pathologists, and they were trying to understand risk of prostate cancer. And you had an AI model that gives you a Gleason score. So this is a score that gives you, the risk of prostate cancer. I don't remember the range of the score, but it's not a 0 or 1 score. And they asked people before they interacted with the AI, what do you want to know about it? So this is pre-probe questions. Then they had people interact with the AI and make predictions. And then they had people ask it, after they made predictions, what would you have wanted to know after you made decisions with AI? And we're going to try to summarize what they learned from this study. So the first thing the pathologists wanted to know is, what was this model trained on? What was the size of the data set? So they would hope that the data size is larger than what a pathologist would see normally. Then they wanted to see where this data come from. So did it come from a single hospital, from multiple hospitals, and so on. And then they wanted to know what was the input to the model. Did it just have access to the image, or did it have access to more modalities? And that would comfort them more and so. What's the solution to this? One way you could do this is to present the pathologists with something called the data card. So this is something that's gaining more and more popularity. And it's basically a very formal description of a data set. So this is a bit unclear here, but this is from Google. So this is the data cards playbook. And it tells you when you have a data set, how should you describe it and what information should you describe in this data set before you release it to the public. So that's kind of one solution to the pathologist demands. The other thing the pathologist wanted to know is how the AI was making its predictions. Was it relying on color? What else was it relying on? Does it take into account the relationship between this biological phenomena and this biological phenomena? So what is the model thinking? Other things they wanted to know is, where did the model have its ground truth from? So this is something very important. When we train models, we usually have our features and then our labels. Our labels come from somewhere. In chest X-ray example I gave in the beginning of lectures, you had the radiology reports, and then we extracted the labels from them. So those were noisy labels. I could have trained the model to just predict on the data of a single radiologist. So I could have it mimic radiologist prediction, and that's the model ground truth. And they really want to know what is its source of ground truth. Now, other kind of information they want to know is the model's point of view. So this is a quote. So they know what my friend would call this case, but what would the AI call it? If I'm thinking about it as a peer, what is its kind of differential diagnosis process? How is it thinking about things? And they really wanted to calibrate their understanding of the AI by kind of interacting with it. So they wanted to see ground truth, what they would have predicted and what the AI would have predicted, just so they can calibrate their understanding. I've done some initial work on this area as well. So this becomes a process of doing the following. This is kind of your data space. And what you really want to do in this data space is you want to cluster the space into cases where the AI is better than the human and the human is better than the AI. And then you could show these regions to the pathologist, and they would understand kind of the calibration of the model and how it compares to them. We've done some user studies where we show people these regions and have them predict, and then we don't show these people these regions and just have them predict tabula rasa. And kind of on some question answering tasks and more tasks, this kind of onboarding process really helps people sometimes. So moving on, they also wanted to understand how does the AI improve of different AI over previous AI models. How does the AI decision boundary was set? So what is its false positive rate? What was its threshold? What point on the AUC curve did we choose when we deployed this model? So they want to know all that information. The last set of pieces they wanted to know is the accuracy and performance of the model. So how do you define accuracy, first of all? The pathologist thought that this model was predicting benign or cancer. And in fact, the accuracy that was computed was based on the Gleason score. So if you just show them an accuracy, you really need to tell them, what is this metric you're defining? And then you want to compare the accuracy to baseline pathologist accuracy, as we did previously. So this model is 90% accurate. But what is the pathologist accuracy to begin with? Is it 95? Is it 85? And that really helps the pathologist know when to trust it. And then finally, you want to report AI performance on subcategories. So how well does it do on women, men? How well does it do with people with these kinds of things versus the others? So kind of on subcategories you can define. Another way you can kind of solve this is with model cards. This is also gaining popularity. This is another example from Google for an object detection model, where not only do they just report AUC accuracies, they do deep dive investigations of where the model fails and describe them. If you've seen the GPT-4 report yesterday, there was another paper called System Card that was beyond the original report, and that explained where does it do well, where it doesn't do bad. So these things are kind of gaining popularity when you release models. So all right, so we've talked about how we can have people learn better mental models. We're going to go back to our two main sins, over-reliance and under-reliance. So I'm going to redefine over-reliance. if you give me an AI model and you tell me it really does better than human assistants, I have an incentive to almost always rely on it since it's better than me. You define over-reliance as when you rely on this model even when it's inaccurate. So you're over-relying on it more than you should. And one reason I think this happened, we'll see this, is misleading explanations. So hopefully in a future lecture, we'll see things like LIME and saliency maps. These are things which are great for model debugging, but when you present them to people, you often see worse behavior than if you did not present these explanations to begin with. And there are many pitfalls to them. So we'll start with this case study. They had almost 220 clinicians try to recommend between different antidepressants. So they would show them a person's information. Then they would tell them the model predicted this specific antidepressant. Then they would show them what features contributed to this model's prediction. So they show them this kind of visual, and you can see, the model prescribed this specific antidepressant because the patient had diabetes, high blood pressure, and because of their prior SSRI non-response. So different features. When you look at the results, you get this picture. So y-axis is accuracy. X-axis is different configurations of the human AI team. So the baseline performance is the clinicians alone. So this is 0.36. Our AI model, fantastic, 0.66. When you have the clinicians with the AI without any explanations, when the AI is correct, they do better than the clinicians. But when the AI is incorrect, you're doing worse than the clinicians on their own. The problem is when you show the clinicians explanations beyond just the AI predictions, they do even worse. So you gave them more information about why the AI made its decision, and you're getting worse results. So when the AI is incorrect now, the performance goes from almost 0.3 to 0.6, 0.3 to 0.26. So that's kind of a drop just due to explanations.
I'm having so much trouble understanding this because AI alone is at 0.66.
Yes.
So in a way, the fraction in which the AI is incorrect is only a third. And yet, when you combine clinicians and AI, you're basically saying, so my question is the second green curve for the subset of cases, i.e. the 30% of them?
Yes.
Got it.
Yeah, and we show them two.
Cases.
Yes. So this is for 60% and this is for 40% almost.
Got it.
Yeah.
So basically, for the 60% of cases, you've now brought it from 100% accurate to only 40% accurate.
Exactly.
So the third is just a major drop on where the AI would. But I'm also curious about the Venn diagram of when is the AI correct versus the clinician. Do they agree in the ones that they have incorrect, for example?
So can you just repeat that one more time?
So if you look at the Venn diagram of how much does the correct prediction of the doctor and the AI overlap?
Are they the same? Oh, okay.
Yeah, basically, like in that 30% where the AI is wrong, what's the clinician's outcome? Do the clinicians get any of those correct?
Right. That would give us a better picture. Yeah, that makes. But from this picture, what we can see at least is when the AI is incorrect, you go from 0% to 30%. So that's kind of, you're mitigating some of that harm. But that does not tell you the specific question you answered.
Yeah, but conversely, when the AI is correct,
you're
100%,
yeah.
24%.
Yeah, but the problem is you never know when it's accurate or inaccurate. If you have that knowledge, then you would be great.
So this is sort of a comment. 50 years ago, people worked on expert systems that were based on logical criteria or Bayesian methods or something. And we worried about the question of what happens if the AI how much would it mislead people? But experiments like this had not been done, and so this was all speculative. But the speculative assessment was that if the AI was really badly incorrect, then it wouldn't harm anything, because the doctors would say, oh, this is really screwy, it's just blown it. And the problem case is when it was only slightly wrong. Now, I don't know if
they're flipping the prediction, thinking that it's wrong, and that basically pushes it way worse than if you just flip at random or always trusted it.
Yeah.
Wow. So if the AI was only less good, then we'd be doing better overall.
Well, I mean, if the AI
Because you'd be
were
flipping
terrible,
the result of the AI.
if the AI
less
were
often.
terrible,
Yeah.
then the doctor would decide never to use it, and
Yeah,
so it would be a no-op.
Yeah.
If the AI were sometimes good and sometimes bad, then it's really a problem, because it depends on how well the human being can figure out how well the AI is doing, which is relevant to this previous experiment.
The way that I see it is the third option, where we are currently hitting the uncanny valley.
Yeah.
So I don't know if you guys have heard about the uncanny valley, but in comics, in illustration, etc., if you're very far from a human, like you just have a circle and two eyes and a smile, then people are very comfortable with that. The closer and closer you get to human, the more comfortable they are. But if suddenly you have a smiley face with very realistic skin of a human, then it's like too close but not quite there, and then it's this uncanny valley where suddenly like the comfort with the drawing becomes like plummets prior to becoming, wow, that's actually human. So in a way, the uncanny valley of AI would be when it's very good but not quite perfect, and you start mistrusting it to the point that you'll flip a very frequently correct answer, and that sort of might be dropping it.
How many of you have seen the Polar Express movie?
Yeah, exactly.
Okay, that's the uncanny valley.
All right, so in this case, we saw that explanations were hurting. The way to fight this is design explanations with clinicians in mind. So bring in clinicians to the design of your AI systems, to the design of the interfaces, and to the design of the explanations. So this is another study with the radiology example as well. And what this team did is the following. They brought in a bunch of radiologists. They had surveys for them. They asked them, what would you like to see from the AI predictions? Then the team went and built sketches of possible interfaces. And then they iterated this design. So they kept, they had this iterative design process with sketching, asking the radiologist again and repeating it until they converged to a final design. And in the end, the radiologists wanted 8 different explanations from the model. And these include the following. So number one is they wanted to ask questions of the model. So they wanted to see what in the radiology image contributed to this diagnosis versus that diagnosis. Second, they wanted to understand how different predictions of the model interact with each other. So if the model had said this patient has pleural effusion and this patient has edema, both of these predictions contribute to the final prediction of patient having pneumonia. So how do the different predictions interact with each other? Third, they wanted to see contrastive examples. So if they zoom in on a specific part of the X-ray, they wanted to see what it would look if it was healthy versus unhealthy. So allowing that kind of questions. And finally, they wanted to understand how did the model's predictions change over time. So often in radiology, you have a prior diagnosis. So 6 months ago, the X-ray, what changed from 6 months ago? We know that now you have atelectasis. Did you have it 6 months ago as well? So is it a new finding or not? So all of that kind of different information. And you take these sketches, and then you go and build very fancy user interfaces. And these fantasy user interfaces, you already know that the clinicians buy into them. The clinicians want this technology because you designed it with them in mind. We will talk more about this philosophy of human-centered design. Yes?
Like, systems like this been implemented in any hospital in the US? Like these sort of AI systems?
Yeah, this is, for breast cancer at least, it's been implemented here in Boston, I believe. Regina Barzilay has done it a lot, has done some work there. In Europe, they've done a lot of these also for breast cancer. I don't remember the specific ones for chest x-rays, but I know for breast cancer, they have these kinds of interfaces. And
For diabetic retinopathy.
diabetic retinopathy for sure, yeah.
So hospitals actually have some of these systems.
Yeah. You know, very kind of interfaces where you can ask more questions than just predictions. And they're being implemented.
But just to clarify, but that's not commercialized, it's research-based, or is it commercialized?
Commercialized. Eric says commercialized. There's also research as well.
But they're a lot slower, and there's tons of companies doing this type of work.
I don't have the latest data, but the last time I looked, FDA had approved something like 35 AI-based applications, machine learning-based applications for clinical use. So, and those are typically done by commercial companies because they're the only ones who could afford the testing to convince FDA to let them do it.
Quick follow-up question.
Yeah.
Peter, I was wondering, so what's like the typical timeline for the FDA approval of AI systems like this?
So in early April, we're going to have a bunch of people from the Boston University Law School come in and give an entire class on the FDA approval process and how to think about that. So let me defer your question to that.
Perfect. One thing I like to do is debunk saliency maps. So this is one of the most famous forms of AI explanations. There's multiple methods to do this: integrated gradients, GMAP, I have no idea. And they're really not helpful. I have not seen a single paper that has implemented them, and there's many that have, not just in healthcare. An image classification task show that these are helpful for people. Almost in all of these experiments, they're not helpful. They could be helpful for model debugging, seeing if your model is relying on spurious signals. But other than that, kind of not at all. So that's why you need maybe more sophisticated explanations. Let me get to the, yeah.
Okay, unless you're running short.
No, we have time.
So we ran into an amusing example where we were doing some saliency maps to try to understand what part of chest X-ray images a model was intending to when specifying these same textbook labels on the images. We were using a different data set from theirs. And one of the things that was funny is if you had a report that said this patient does not have pleural edema, for example, what would you expect the attention now to focus attention on when the answer is it's not there? So I would have thought it would be the entire image, but in reality it was something very strange. It was all the parts of the image that were not the patient's lungs, which is sort of a weird way of it trying to tell us that there was no evidence in the lung or something, but that was weird.
Yes.
Why do you think it is that saliency maps don't help? If the model actually does perform well, it's looking at the right regions.
So let's decouple two things. So are saliency maps really telling you where the model is looking at? So that's one question. The other question is, if they are, is it granular enough? Is it helpful? And I think it's a mixture of both. First, that some of the methods are not really showing you what it's really looking at, because they're looking at gradients, and maybe the gradients are not revealing enough information. So that's the first pitfall. And then the second one, I really don't know why. I really don't know why beyond just, we tried it, it didn't work. I think that's enough evidence. And even in kind of on generic classification tasks, I really don't see the benefit from it too much. So, but yeah.
Again, one could argue that knowing that it's at least paying attention to the lungs makes a difference.
Well, it definitely helps in debugging.
Yeah, debugging.
Yeah, exactly.
If it's paying attention to the label on the side of the X-ray, then you know that you did something wrong.
And I ask my students to do this all the time, to basically say what part of the model, like, show me where it's, where the data is coming from. And I agree with you that sort of,
debugging is good.
It's in there.
But what in there? That's the question, I think.
Well, you want to know that it's not grossly.
Yeah, exactly.
Because that's the problem with AI. Basically, we very often criticize AI for not having common sense.
Yeah.
And I think knowing that it's in the lung at least tells you that it's in the right ballpark.
Exactly. Yeah, that's fair. But it also helps you mislead you. You think, oh, it's looking at the lungs.
It's in the lung, so it must be good.
Yeah.
Yes,
So that's the counterpart to that question.
Yeah, that I agree with. Basically, that humans are perhaps not a very good judge for, at least it's not grossly wrong, so it must be right.
Exactly.
And I think there's, basically there are rhetorical ways of winning arguments by sort of saying some things that are correct. So you're winning at least the trust of the third party that's listening in.
Yeah.
Even though what you're saying is kind of like overall BS. By sort of saying a few things that you've kind of heard about, you're like, oh yeah, I've heard about that.
Exactly.
And you're kind of winning points, and maybe that's sort of your criticism that
Exactly.
you can win points too easily by being vaguely in the vicinity of the lung.
Yeah.
Got it.
Yes?
So I've always thought of Samson maps as being really helpful. So what do you do you have a another method that you prefer in the end?
I think if we go back to the
Can I rephrase what you said, maybe to sort of reconcile with my view as well, which is that when the model is grossly wrong, they're very helpful because it tells you that they're way off. But when they're not way off, then they're not offering additional help. And in fact, they might offer false confidence that just because it's somewhere in the lung, you're like, oh, cool, now I can trust this model. But in fact, no, you could be in the lung and it's still wrong. That's my interpretation.
Yeah. I think literature is heading towards different directions. One of them is detecting concepts from the images. So these works on something called concept bottleneck models, where you go from image to a set of concepts describing, biological things or things in the image, and then from these concepts to your final predictions. And then now to understand why you made this prediction, it's because you predicted these concepts. That's kind of something gaining popularity. That's a bit more interpretable. And the other part are contrastive explanations, where you just try to see what would it look like if it was healthy, and that would help you pinpoint exactly. But yeah, other than that, I think there's still lots of research to be done. These are just kind of some pointers.
There are a lot of ideas, but I don't know that I have a good answer to your question.
Yeah.
So, for example, there are people who looked at, these very deep models and said, well, maybe the right thing is not to look at where the top layers are paying attention, but maybe somewhere in between, because we have this sense that these multi-layer models are abstracting from the raw data up to some final decision. And so maybe there's a layer in there that is attending to things that are meaningful in that process, and those may be more helpful. And so I've seen papers that do that, but I'm not convinced that that's the answer either.
Yes?
So hopefully this question isn't draw Peter's draft,
It's an AI draft.
Yeah. So body of research, or will we get to a lecture where there's showing that AI can actually do a better job than doctors at some point?
I don't think I follow your question fully.
So in the first slide you
Yeah.
showed human accuracy,
Yeah.
AI accuracy, and then AI plus human
Yep.
accuracy. The AI accuracy was still higher
Yes.
than the human, or the human plus the AI. So I'm wondering if there's a body of research happening in that category that sort of shows, rather than make a design
Yeah.
with the human, why don't you just design it with the human outside of it?
Yeah, that's like the numbers I gave in one of my first slides. So, but these are real numbers. So the AUC is actually higher for the models for the X-ray images.
So are there people researching to show that if we actually remove doctors from this workflow and just use AI, it'll be a better outcome?
I mean, I don't think we have done research about better outcomes. There are some research from these breast cancer results where you show that AI can catch some people that the doctors would have missed. But in the narrow sense of like, I have a test set, my model is performing better than radiologists, we have those results. Nobody has done I don't think has done like the trial where you completely remove radiologists and you just give the physician the AI's prediction. I don't think someone has done the full loop.
Never happened.
Well, may have never happened.
The beauty of these models, not just like in the last few years, but over the last few decades, is that starting to treat the human as yet another predictor rather than the ground truth, I think is what is the only way to move the field forward. Basically, if you think of the clinician as infallible and the AI as something that you should always treat with mistrust, then you're going to hit this uncanny valley the way that we've labeled it, even though that's not the correct term. But basically, I think that the moment you can kind of abstract away and sort of not have this very human-centric, oh, the AI must be wrong or dangerous, et cetera, approach, but treat them both with the same trust and distrust, I think that's probably the way forward. And I agree, I think Eric or someone said, it ain't going to happen. In other words, it's going to be very rare to take the human out of the loop. But we have to put the right safeguards, kind of like in the Turing test, where it's behind a veil and you kind of take that mistrust away. I don't know if that's what you meant.
I just meant you're going to get sued.
No, the keeping the human out of the loop is dangerous for the company developing the AI because suddenly they become the person to sue.
Yeah.
If the AI is there but the liability lies with the doctor, the AI system the AI producers will prefer that, even if it means it's more risky for the patient, because you're sort of offloading the who gets sued part. Is that okay? Yeah, that's exactly right. Yeah.
Sounds good. Thank you.
But we might need new laws where you don't blame
Yeah.
Tesla for accidents, but you blame the driver, which I guess is what Tesla is basically saying. Like, keep your eyes on the wheel. This is not a self-driving car, even though it might actually be safer than humans. They just don't want to get sued.
And even though they advertise it as a self-driving car.
Yes, yes.
All right, so one of the last things we want to talk about is under-reliance. So this.
But I have to say that at some point, the difference in accuracy will be so blatant that we as a society might need to sort of change the way that we perceive these, change the laws for who get sued, etc.
Yeah.
Basically, we're kind of in this funny zone right now where it's kind of almost on par. At some point, AI might be way better, and then I think society will kind of follow along.
All right, so the last part is about under-reliance. This is another study in a real, I think in the ICU, or where you have different clinical decision support systems which trigger alerts. And these are alerts for whether the patient is allergic to a specific medication or drug, whether if you prescribe this drug, it will have a bad interaction with another drug. So there's multiple types of alerts. And this table is showing you how often are these alerts, how often do they happen, how often do the physicians override the alert. So they just press cancel alert. And what you see is almost 50% of alerts are overridden. But what you really need to understand is, was it appropriate to override these alerts? For many cases, so this next table is showing you, for some of these alerts, it was correct to override them. For some of them, it was less appropriate. But on average, the overriding was 50% accurate. So 50% of the time, you overrode an alert, and it was not the best decision to make. So kind of half of alerts were overridden, and half of the overrides were actually appropriate. But what's happening here, what's happening is really alert fatigue. You're just putting on too much alerts, and the physician might be just fatigued because of them and might not even look at them. They're just, you give me alert every single hour. I'm not gonna even look at you anymore.
You're just training the user to sort of very rapidly click the button wherever it appears.
Exactly. So what can we do to mitigate this? We really want to make it easy to override, as easy as possible, clicking an X. We want to have feedback in the system. If you override something, tell us why, so we can adjust to this. We also want to adjust to each physician's alert override rate. So maybe some people only want to be alerted when it's really critical, and that's the only time they will look at it. Maybe other people want alerts all the time, and they always look at them. So having this personalization of your alert threshold is really important. Finally, you want the model to adapt to the user. So if you told the model, oh, I overrode this because you're always wrong on these things, users expect feedback. The clinicians expect feedback from the model and expect it to improve over time. And if you do improve it over time, you want to let people know. So if you update your model, update your alert threshold, let people know because they're not used to it, and that's really important. So I'll finish off with some takeaways.
I just wanted to Google Homer's typing verb for the episode where Homer Simpson figures out that just pressing Y all the time is the right thing. Anyway, sorry.
So another anecdote. So David Bates is head of general internal medicine at the Brigham, and this was years ago, but they ran into a problem where there was a company called First Data Bank that created a drug-drug interaction database that they sold for lots of money by reading the literature and compiling this table of all the drugs that could potentially interact with each other. And there were tens of thousands of these interactions. And so at the Brigham, they decided to install this system, and it alerted doctors whenever they described some drug that interacted with some other drug that the patient was already on.
In other words, all the time.
In other words, on almost all the cases. And eventually the doctors threatened David with throwing him out the window if he didn't stop this system. And so they looked at why was this happening. And part of it was that the system's knowledge of what was happening to the patient was incorrect. So for example, doctor orders a drug to a patient, it gets sent up to the ward, but by the time it gets there, they've decided not to give the drug. Now, if they were perfect, they would go into the pharmacy system and say, this drug was not given, but they don't bother doing that, they just throw it away. And of course, charge the insurance company for it. So that was one problem. The other problem is like what Eric was saying, which is that First Data Bank wants to be absolutely thorough because they don't want to miss an interaction that they should have caught, which harms some patient, for which they're going to get sued for providing bad data. And so their incentive is to be absolutely comprehensive. But in reality, it's impractical to get warnings on every single case. And so David actually convened a panel of doctors from the Brigham, and they sat down and they said, okay, what are the top 20 drug-drug interactions that we actually observed? And they threw out their monitoring system and just kept those 20. And then everybody was happy.
I think I may have mentioned this before, but one of the sentences that bothers me the most is when they start with, out of an abundance of caution, dot, dot, dot. And that basically means we don't do a cost-benefit analysis. We just look at the cost. We just look at the risk. We don't look at the cost of mitigating the risk. And I think one example is canceling our lecture on Tuesday. MIT shut down out of an abundance of caution. And then my kids were like, is this what we shut down for? And so again, school gets like the teachers canceled the school for my kids like last week as well. And they're like out of an abundance of caution. The next morning there's like no snow at all. So again, we should always say, what are we preventing from? What is the actual risk? And what is the cost associating with sort of preventing something to avoid risk? And very often when we do that analysis, we realize that taking some risks is okay.
Right, I think we're out of time. I just want to end with this nice slide about different guidelines for human and AI interaction when you build these systems, when you integrate them, and over time. And if you want to learn more about this area, feel free just to talk with me. And thank you all so much for today.
Save my precious laser.
Oh, yeah.
Now you know what you might do with it.